Fire has shaped human civilization for thousands of years, from warmth to survival and eventually to industry. Today, that ancient power begins not in a flame, but in carefully managed forests. Match factories prefer softwoods like aspen and poplar. These woods burn predictably, produce minimal smoke, and split cleanly under high-speed machinery. Hardwoods burn too hot. Resin-heavy woods burn unevenly. In mass production, consistency is everything. Modern logging machines cut trees with millimeter precision. Clean cuts reduce fiber damage inside the wood, critical for matchsticks that must survive extreme processing speeds later inside the factory. Before entering the factory, each log is scanned. Diameter, straightness, and internal density are measured using laser and pressure sensors. Any irregular grain could cause splintering, wasting thousands of matchsticks per minute. At a microscopic level, wood is a bundle of hollow fibers. Even spacing allows flame to travel smoothly. Uneven grain creates unpredictable burning, something a match factory cannot afford. Fresh wood contains up to 50% moisture. For matches, that number must be carefully controlled. Too wet and the flame struggles. Too dry and the stick burns too fast or snaps during production. Only after passing strict inspection does the wood enter the factory. What follows is a transformation, from raw tree trunk to thousands of identical matchsticks every minute. In the next stage, speed, pressure, and precision take over, where wood begins its journey toward becoming fire. Inside the factory, chaos is the enemy. Before any cutting begins, logs are automatically aligned. Even a few millimeters of misalignment can cause uneven peeling later, leading to broken splints and massive material loss. Debarking drums use controlled abrasion, not cutting. Bark is removed without damaging the softer inner wood fibers. This matters, because damaged fibers weaken the matchstick before it's even formed. Once stripped clean, logs are inspected again. Any remaining knocks or surface cracks can cause tearing during peeling. At production speeds reaching thousands of sticks per second, there is no room for error. This is the heart of matchstick production. The log spins while a fixed blade peels it like paper from a roll. Blade pressure, angle, and speed are precisely calibrated to produce veneers thinner than a few millimeters, without tearing. Laser sensors constantly monitor veneer thickness. Too thick, and the match burns unevenly. Too thin, and it snaps during handling. Precision here determines the quality of millions of matches downstream. The veneer is sliced into splints at extreme speed. Each blade must stay razor sharp. A dull blade crushes fibers instead of cutting them, creating weak points that break during later chemical dipping. At full capacity, a single line can produce millions of splints per hour. Every second of uninterrupted flow means efficiency. Every jam means fire risk, downtime, and loss. Now shaped, but still raw, the splints are far from finished. Before they can safely carry fire, they must be dried, stabilized, and chemically prepared. Freshly cut splints still hold internal moisture trapped inside their fibers. If ignited now, they would smolder, crack, or fail completely. Drying is not about speed, it's about control. Drying kilns use forced hot air circulation, not open heat. Temperatures are carefully maintained between 80 to 110 degrees, hot enough to evaporate moisture, but gentle enough to prevent warping or brittleness. As heat penetrates the splints, water molecules escape from microscopic wood cells. The goal is balance. Final moisture content must drop to below 8%, the ignition sweet spot. Infrared sensors continuously scan the splints. If moisture rises even slightly, kiln airflow and temperature automatically adjust. This closed-loop system prevents entire batches from failing. Next comes paraffin wax treatment. Wax acts as a fuel extender, allowing the flame to travel smoothly up the stick. Without it, the match would burn weakly or extinguish mid-burn. Ironically, matches also need fire control. Ammonium phosphate is added to slow down combustion. This ensures the match burns steadily, without flaring dangerously or breaking apart. After chemical treatment, splints are dried again. This locks the chemicals into the wood fibers, creating a controlled burning structure ready to accept the match head. At this stage, the wood is no longer just wood. It's a precisely engineered fuel carrier, ready for the most delicate and dangerous step of all. This is where wood meets chemistry. The match head is not a simple coating, it's a carefully balanced chemical system. A mistake here doesn't cause defects, it causes fires. The modern safety match head contains no phosphorus. Instead, ignition relies on potassium chlorate for oxygen, sulfur for fuel, powdered glass for friction, and binders to hold everything together. At the microscopic level, these particles must be evenly distributed. Uneven mixing causes delayed ignition, or worse, uncontrolled flare-ups. Mixing happens slowly. High-speed agitation creates heat, and heat creates risk. Viscosity is tightly controlled so the match head forms evenly without dripping or cracking. Even a few degrees of excess heat can destabilize the mixture. Cooling jackets circulate water to keep the compound chemically dormant until the moment of ignition. Once mixed, the compound moves immediately to the dipping line. Time matters. If it thickens too much, the head becomes brittle. too thin, and it won't ignite reliably. Every second, sensors watch for abnormal heat, vibration, or pressure. In a chemical environment like this, automation isn't optional. It's survival. The chemistry is ready. Now, precision motion takes over, where thousands of matches receive their flame, one synchronized dip at a time. This is where chemistry meets choreography. Thousands of splints move together, timed to fractions of a second. At this speed, precision is not a goal, it's a requirement. Each splint is locked into a steel frame. The spacing is exact. If two sticks touch during dipping, their heads fuse, instantly scrapped. Machines eliminate what human hands never could. The first dip forms the core. Depth and withdrawal speed control head size. Too deep, and the match burns violently. Too shallow, and it won't light at all. Centrifugal force does the shaping. The rotation removes excess compound, forming the familiar rounded head, identical across millions of matches. Before the next dip, the head must partially harden. This prevents cracking while still allowing layers to bond chemically. Many factories use multiple dips. Each layer improves ignition reliability, burn stability, and shelf life, especially in humid climates. Under magnification, perfection is visible. Uniform texture ensures consistent friction and predictable ignition, match after match. The flame is formed, but not yet tested. Next comes the moment of truth, where every match must prove it deserves to exist. By now, the match looks complete, but appearance means nothing. In mass production, only performance matters. This is where every batch must earn its release. Machines strike matches with controlled force and speed. Too much friction would mask weak chemistry, too little would cause false failures. Each strike is identical, removing human variability. Burn time is critical. Too fast, and fingers get burned. Too slow, and ignition becomes unreliable. Sensors measure flame duration down to fractions of a second. A match head must survive transport, humidity, and rough handling. These machines simulate weeks of stress in seconds, exposing weak bonding instantly. Matches are shipped across continents. Climate chambers simulate tropical humidity and cold storage to ensure ignition works everywhere, from dry deserts to monsoon zones.
Ironically, match factories are among the most fire-protected buildings on Earth. Every line is isolated. Every zone can shut down instantly.
Automation catches patterns. Humans catch intuition. Final approval still depends on trained eyes, because safety is not negotiable.
Only after passing every test does a match move forward. What survives this stage is ready to meet the world.
A match is useless without control. The box is not packaging, it's a safety system. Everything starts with engineered cardboard, chosen for strength, flexibility, and friction tolerance. Steel dies cut thousands of box blanks per minute. Tolerances are tight. A loose box spills matches. A tight box prevents smooth striking. Automated arms fold, glue, and press each box. Adhesives are chosen to withstand heat and humidity without releasing fumes that could contaminate the matches inside. Unlike the match head, the striker contains red phosphorus. Kept separate, it remains stable. Only friction converts it into reactive white phosphorus, momentarily, during striking. Thickness matters. Too thin, and ignition fails. Too thick, and sparks become unpredictable. Machines regulate layer depth to microns. The striker must cure slowly. Rapid drying causes microcracks, reducing friction reliability. Time here equals safety later. Only now do matches and boxes reunite. Two halves of a controlled ignition system, designed to work only together. From forest to friction, every detail leads here. But before these matches leave the factory, one final system takes over: logistics. Every matchbox is counted with mechanical precision. Cartons must contain exact quantities to meet regulations and ensure consistency worldwide. Millions are counted daily with zero margin of error. Sealed cartons preserve product integrity. Labels carry crucial data: batch numbers, expiration info, and origin codes, linking every match to its production line for safety and traceability. Even after packaging, storage conditions matter. Controlled humidity prevents premature head degradation. Controlled temperature ensures long shelf life without compromising ignition reliability. Pallet wrapping stabilizes millions of matches for shipment. One wrong movement during transit could damage thousands of sticks. Automation ensures consistency. From factory to market, matches travel globally. Efficient loading systems prevent damage and ensure timely delivery, often to regions with challenging climates. Millions of matches leave the factory each day. From local warehouses to international ports, logistics engineering guarantees safe arrival, maintaining quality across continents. Finally, matches reach regional distribution centers. Conveyor systems sort and route them efficiently to retail stores, ensuring that a single spark can be safely delivered to millions of households worldwide. From the quiet forest to high-speed factories, every detail ensures a simple act, striking a match, is safe, reliable, and controlled. Fire, humanity's oldest tool, delivered with modern precision.